Hi everyone, Mr. Kwan here. Today we're going to be talking about continuous functions. A continuous function is basically a function such that when you draw its graph, you don't need to pick up your pen or pencil to draw it. Now let's talk about continuity at a specific point. If you have a function f, it is continuous at the point x equals c if all of the following conditions are satisfied. The first condition is that f of c exists. The second condition is that the limit as x approaches c of the function f of x exists. And the third condition is that both of those things are equivalent to each other. If one or more of the conditions above do not hold, we say that the function is discontinuous at x equals c. If a function is discontinuous at one or more points, it is called a discontinuous function. Polynomial and rational functions with regards to continuity have some special rules. So those rules are every polynomial function is continuous for all real numbers, and every rational function is continuous at all values of x, except those that make the denominator 0. So example 1 says, for what values of x, if any, are the following functions continuous? So we have our first function, h of x equals the quantity negative x plus 9 divided by the quantity 3x minus 10. Now, from the rule above, this function is going to be continuous everywhere except where our denominator equals 0. So it turns out what you can do is you can actually set the denominator equal to 0 and solve for the x value that will make the denominator 0. So I'm going to take our denominator, 3x minus 10, and I'm just going to set it equal to 0. And from here, I'm going to add 10 to both sides, and then I'm going to divide 3 on both sides. So we end up getting x is equal to 10/3. And so what that means is h of x is continuous for all values of x such that x does not equal 10/3. So at every other value of c, or every other value of x, our function is continuous except at x equals 10/3. So let's do the same thing for part b. We have the function f of x equals the quantity x squared minus x plus 2 divided by the quantity x squared minus 49. We're going to set our denominator equal to 0 again. So we have x squared minus 49 equals 0. And I'm going to add 49 to both sides, so we get x squared is equal to 49. And then if I take the square root of both sides, we get x is equal to plus or minus 7. Therefore, we would say that f of x is continuous for all x such that x does not equal positive or negative 7. So that is our answer for example 1b. Example 2 says determine the values of x, if any, for which the function f of x defined below is discontinuous. Now, here we have what's called a piecewise function. And this particular piecewise function is made up of two subfunctions. So the first subfunction is x squared, and the second subfunction is the square root of x. Now, x squared is a polynomial, is an example of a polynomial. And recall from an earlier rule, we said that polynomials are always continuous for all values of x. And if you recall from a previous class, the square root of x, if you have your y-axis here and your x-axis here, the square root of x, the graph looks something like that. And so it turns out that if you have this function y equals the square root of x, that is also continuous for all values of x that are greater than or equal to 0. And so the only place that we might have issues then based off these intervals here is the value of x equals 1. So what we're going to do is we are going to see what the value of 1 is at each of those locations. And so let's plug in 1 into the first function. If we did that, 1 squared is equal to 1. And then in the second subfunction, if I plugged in the square root of 1, that also gives us 1. So therefore, basically the function is continuous at x equals 1, and therefore it's continuous everywhere. Now, if I were to sketch the graph of this, here's x equals 1, here's y, here's x. So everywhere before 1, it takes on the graph of y equals x squared, which looks something like this. And this is a really rough sketch. Remember, it's a parabola, so our parabola looks something like that. And then everywhere 1 and later on the x-axis, our graph takes on the form of the square root of x. And so I'm going to plug in that hole right there, and our graph is going to look something like that. And so notice that if I were to draw this from left to right, I would not need to pick up my pen or pencil in order to draw the graph here. And so because that's the case, our function is continuous everywhere. So we can say f of x is continuous for all values of x. Find the numbers at which the function below is discontinuous and graph the function. So kind of like the previous example, we have a piecewise function here, and all of the subfunctions of our piecewise function, in this case, they are all polynomials. So the first and third subfunction are linear functions, and the middle one is a quadratic, which are all examples of polynomials. So they're going to be continuous everywhere except possibly where we are changing subfunctions. So on these intervals is where we want to check. So it might be helpful to start and think about the graph first. When x is less than 0, we have the function x plus 2, which is a linear function with a slope of 1 that starts at the y-intercept of 0, 2. So I'm going to place, let me switch colors. So I'm going to place an open circle at 0, 2, and then draw some points there to create my line. So we know that anywhere when x is less than 0, our function is going to look something like that. Then if I look at my middle subfunction, we have 2x squared, and that's for when x is between 0 and 1. So let's see, if I evaluated 2x squared at x equals 0, then that would be 2 times 0 squared, which equals 0. So that would be there. And then let's plug in x equals 1. So that would give us 2. So that would be right there. So our function looks something like that. It's a very small portion of the parabola. And then when x is greater than 1, we would have negative x plus 2 or 2 minus x, whatever you want to think about that. So I'm going to plug in 1 there. So 2 minus 1 is equal to 1. That means that there would be, it's kind of hard to draw this. There would be an open circle at 1, and it has a slope of negative 1. So that would be like that. And then let me just pull out my ruler again to connect those. And then that graph would look something like that. So Now pause the video for a moment and ask yourself, where do you think our function is discontinuous? So it actually turns out that f of x is discontinuous at x equals 0 and x equals 1. And let's algebraically kind of show why that is again. So here I have x plus 2, and if I plugged in 0, I'd get 0 plus 2, which is equal to 2. And that's highlighted here at this point here. And then if I plugged in 0 into this subfunction, I'd get 2 times 0 squared, which equals 2 times 0, which is 0. So notice that if I wanted to draw this function from left to right, I'd have to pick up my pencil in order to kind of jump down to the ordered pair 0, 0. And then if I plugged in 1 here, I'd get 2 times 1 squared, which is 2 times 1, which is 2. And then in my last subfunction, if I plugged in 1 here, I get 2 minus 1, which is equal to 1. And notice that these are not the same number, just like these weren't the same number. And so here I would have to pick up my pencil again in order to draw that part of the graph. So at the end of the day, we would say f of x is discontinuous at x equals 0 and x equals 1.